Hello, you're watching Part 10 of Unit 2 of Quick Precalculus Review for Calculus. I changed my mind compared to what I said in Part 9. In Parts 7, 8, and 9 we've been looking at limits, the idea of a limit, and getting more and more rigorous with limits and their relationship to the special number e, which is about 2.71828. And I said that Part 10 we'd go back to thinking about exponential functions and alternative representations of them, and then ultimately on to logarithmic functions after that. I decided in Part 10 that I'm going to stick with limits and the number e for one more video. In fact, I'm going to get fully rigorous with the definition of a limit. There are lots of different kinds of limits. We're going to focus on the limit of a sequence. Alright, that's probably the easiest kind of limit to think about. We'll also visualize limits again, and we'll make use of these Mathematica commands that you see to do this. Is this necessary? Could you skip this? Well, I think it would be good for you to not skip it. I think it would be good for you to watch it and think about what I say. The rigorous definition of a limit is a very, very challenging concept. It takes a lot of time seeing it over and over again and thinking about it over and over again before you really feel like you start to understand it. So you shouldn't imagine that you're going to completely understand what's going on here if you've never seen this before. Right? It is a challenging topic. I think that's worthwhile to start to struggle with before you get to calculus, so that when you get to calculus it might be a little bit easier. Alright? It is also a triumph of human reasoning. You know, Newton and Leibniz, they are considered to be the creators or discoverers of calculus back in the mid-1600s, late 1600s. But they didn't really fully understand it, actually, to tell you the truth, completely rigorously. It took almost a couple hundred years later, until about 1850 or so, when Cauchy and Weierstrass came up with a rigorous definition of a limit. Why did they do that? What's the purpose? The main purpose is to be precise in your knowledge for the purpose of being able to prove theorems in math, related to limits in this case, so that you can be secure in that knowledge and know that it's right. Okay? You really understand something when you make it precise. That's the mathematician's perspective on why it's a good idea. But Newton and Leibniz, like I said, they didn't even know the complete definition. Alright, so what's the situation again that we're thinking about for this definition? We're thinking about this limit that you see right here. Think about r as being a fixed number. What's the limit as n goes to infinity of the expression 1 plus r over n to the n power? It equals e to the r. Alright, this is, by the way, a sequence for fixed r. This defines a sequence being a list of numbers as n is first 1, then 2, then 3, then 4, etc. It takes on positive integer values. What's the limit of that sequence as n gets larger and larger without bound? That limit is e to the r. It doesn't mean the expression 1 plus r over n to the n power equals e to the r. In fact, it never does in this case. There are some cases where it does, but in this case it never does. But it approaches e to the r, as it can be made as close as you want. This absolute value that you see here, representing the distance between 1 plus r over n to the n power and e to the r, can be made as small as you like by taking n sufficiently large. Alright, now we want to get more rigorous with that statement. Let's go on down here to the code that I showed you at the end of the last video. To illustrate this idea, the fact that 1 plus r over n to the n power gets closer and closer to e to the r as n gets larger and larger. Again, for fixed r, the output of this code, it consists of two graphs. The graph on the right is the main one you want to focus on. The graph on the left is just sort of an extra graph to help you visualize the value of e to the r as n gets larger and larger, or excuse me, as r gets larger and larger. Here, for example, I can take r to be 2.44, and you see that the value of e to the r is around, well, about 11.5 or so. You could check that with your calculator. The second coordinate of this point is the value of e to the r for this value of r, and as r changes, it moves. It's the same as the height of this red line that's in between the two magenta colored lines. The value of the y-coordinates of the points on here is the value of e to the r, and that is the limiting value of this expression 1 plus r over n to the n power, as n gets larger and larger. Now we're looking at one dot. We're looking at the first value of the sequence. We're looking at 1 plus r over 1 to the first power, which is just 1 plus r. When r is 2.44, that means the second coordinate of this point is 3.44. By increasing the value of b, we're effectively increasing the largest value of n that we're looking at. When b becomes 2, now we see the first two values. We see 1 plus r over 1 to the first power. We also see the value of 1 plus r over 2 to the second power. And we see that as b continues to increase, those points are getting closer and closer to the red line. I modified the code a bit to make those magenta colored lines, and also to allow this graph to continue going to the right. We seem to have the red line as like a horizontal asymptote or something. Okay? What's epsilon? Epsilon is the measure of closeness. as close as you like, and you can make epsilon as small as you like to reflect the fact that you can get as close as you like. Epsilon goes down in value as I slide this to the right. You can see those magenta colored lines are getting closer and closer to the red line. The point about the truth of this limit is that no matter how small epsilon is, let's pick a particular value, let's pick 0.5, no matter how small epsilon is, you're eventually going to have values, the second coordinates of these dots, that get inside that tube, so to speak, and stay inside there. How big does b need to be when epsilon is 0.5 to get inside the tube and stay inside there? You have to experiment a little bit here. Look at the scale there. It looks like perhaps it's around b equals 40 to 50 in that range somewhere is when you're crossing that magenta colored line and then you stay inside there. You should try that on your own right now. Actually, take your calculator, calculate the value of e to the r when r is 2.44, calculate the value of 1 plus r over n to the n power when r is 2.44 and n is around 40 or 50. You should get a value of that expression that is within 0.5 of e to the r when you make n big enough. Okay? And that is really getting us toward now the rigorous definition of a limit, a rigorous perspective on the reason why this limit is true, first of all. So this is not quite a completely general definition, because I'm still thinking about this example. This is going to give us a completely general definition down here. All right, so how do you phrase it? This is the hard part. You phrase it this way. You say, for any number epsilon greater than 0, there exists a number b greater than 0, so that, think of it this way, the distance between 1 plus r over n to the n power and e to the r is less than epsilon as long as n is greater than or equal to that number b that you found. Okay, I'll say it again. Remember, first of all, the absolute value of a difference of two numbers is the distance between them. So this expression represents symbolically the distance between 1 plus r over n to the n power and e to the r. I'll say it again. For any number epsilon greater than 0, let me add the phrase, no matter how small. That phrase is not necessary for the definition, but it might be helpful for your understanding. For any number epsilon greater than 0, no matter how small, epsilon could be 10 to the negative a million power. There exists a number b. B will have to be bigger the smaller epsilon is. B does depend on epsilon. The smaller epsilon is, the bigger b has to be. The further out you have to go, the larger n has to be. There is a number b so that the distance between 1 plus r over n to the n power and e to the r is less than epsilon as long as n is greater than or equal to b. Okay, let's generalize this to this other situation. It's not much of a generalization. In fact, I can copy and paste this stuff and just modify it a bit. Okay, so xn now is representing an arbitrary sequence. We're going to look at an example here in a minute, this one down here. L is the limiting value of that sequence, the proposed limiting value. What does it mean for this equation to be true, for xn to approach L as n goes to infinity? For any number epsilon greater than 0, again, no matter how small, think that in your mind, there exists a number b greater than 0, you might say sufficiently large, so that, okay, now we need to make changes. The distance between x sub n, the arbitrary term in the sequence here, and L, the limiting value of the sequence, is going to be less than epsilon when n is greater than or equal to b. Okay, so just modify this statement slightly. By the way, you can also understand these statements. It's a good idea to think about, well, what if the limit is wrong? You know, I know the limit of this expression is e to the r. What if you picked the wrong limit, like e to the r plus 0.5? What would happen? Let's see what would happen. So I'm changing the location of the horizontal lines now to be incorrect. Let's increase r again. Now, if epsilon is sufficiently small, you won't be able to get inside the tube and stay inside the tube. Like, for example, I think because I picked 0.5 to add to e to the r, if epsilon is less than 0.5, you're not going to be able to get inside that tube and stay inside of it, no matter how big n is, no matter how big b is. Looks like it might go in the tube, but it never is. In fact, you could keep going forever and ever here, and it would never get inside that tube. Okay, and that's something you could prove. All right, let me make it more extreme. Let's make this a 2 instead of a 0.5. Okay, make r bigger. You're never going to get inside that tube and stay inside that tube. Okay, so it's the fact that e to the r is the correct answer that makes it work. No matter what epsilon is, you're going to be able to get inside the tube and stay inside the tube. These points are approaching the limiting value monotonically. They're increasing. You can have an example like this one where it's not monotonic. Here's my example. Let xn be equal to 1 over n if n is odd, and 2 over n if n is even. You might try to figure out what the values are. In fact, I'll do it here verbally. If n is 1, 1 is odd, so the value is 1 over 1 is 1. When n is 2, 2 is even, so you plug it into this one. 2 over 2 is also 1. When n is 3, 3 is odd, so you get 1/3. When n is 4, 4 is even, so you get 2/4 or 1/2. When n is 5, you get 1/5. When n is 6, you get 1/3. When n is 7, you get 1/7. When n is 8, you get 1/4. 2/8 is 1/4. So this is a sequence. It's going to 0, but not monotonically. It's not a decreasing sequence. It's going up and down, though those up and down motions sort of continue to get smaller and smaller in such a way that this still goes to 0. No matter how small epsilon is, I'm going to be able to have a value of b large enough to eventually get inside the tube and stay inside the tube. So you see up-down motion there, but no matter how small epsilon is, you are going to be able to get inside that tube and stay inside the tube. In fact, that's a good thing to remark about too. Here you're getting inside the tube initially, but then when you get n to be even, you go back outside the tube, but eventually, looks like maybe when n is around, well, around 40 or so, you get inside the tube and stay inside the tube with this value of epsilon and this value. Okay, yeah, with that value of epsilon. Okay. By the way, a little bit of remark about the Mathematica code here. Odd q of n will come back with a value of true when n is odd, and even q will come back with a value of true when n is even. So that allows you, through the use of this symbol that comes from the palette here, by the way, right there, to define this sequence here. And I'll end the video there.